Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC1004, your physical chemistry lab. Today we are going to proceed to our next experiment, which is experiment 5. So the title for this experiment is the molar conductivities of aqueous electrolytes. And the objective of this experiment is to determine the conductivity of various acids and also to measure the dissociation constant of acetic acid. So the details of how the experiment is being conducted has been shown here, recorded by Dr. Faisal. So I hope you will actually watch this video before you actually move on with the slides. Okay, so the essence of this is that you have electrolytes when it's dissolved in water, so you have free ions, and from there you can actually measure the conductivity of the electrolytes. And when you actually have this electrode, so the setup is where you're using the conductometer to actually measure that. And in the video, Dr. Faisal highlighted that the electrode has to be carefully used because it's a very sensitive and expensive probe. So when you actually measure the conductivity of the solutions, make sure that you don't use it as a stirrer, okay, because you might break the sensor. Alright, so when you have electrolytes dissolved in water, so you have these two types of electrolytes, and it can either be the strong electrolytes or the weak electrolytes. So the strong electrolytes are highly dissociated and give solutions with high conductance in water. So example of that will be hydrochloric acid, sulfuric acid, and sodium chloride. And they will usually give you almost 100% dissociation. And due to having this high degree of dissociation, strong electrolytes are good conductors of electricity. And so these aqueous solutions of these electrolytes will have high value of molar conductance. But on dilution, the increase in the molar conductance is small because since they are completely ionized, so on further dilution, the number of current carrying particles does not increase in the solution. Okay, now on the other hand, the weak electrolytes dissociate only partially in aqueous solution, and so you can expect it to have a less than 1 degree of dissociation. So the example that we are going to use in this experiment will be the acetic acid. Okay, and the molar conductivity for these weak electrolytes increases rapidly on dilution or with decreasing concentration. All right, so in this experiment, this Onsager equation will be employed to determine the molar conductivity of the given electrolytes. Now, I'm not so sure whether you have covered this in your lecture, but if you have, that's good. So this is now the practical side of it. So using the Onsager equation, we can actually measure the lambda naught, which is the molar conductivity at infinite dilution. So you have here, you're going to measure the conductivity, and from there you can actually find the molar conductivity, and from the plot that you're going to construct, we can actually get this lambda naught. Okay, and C is the concentration of electrolyte. So then the molar conductivity is defined as the conductivity that you measure you find the average, you measure it 3 times as shown by Dr. Faisal, and divide that by the concentration of the each of the solution prepared, and from there you get that. Okay, and from this So when you construct the molar conductivity versus the square root of the concentration, so if you rearrange this equation, so you know that this is a straight line, then you have this negative beta as the gradient, and you have the intercept at y-axis is where you will get the molar conductivity at infinite dilution. So straight away you can get this value from your plot. Okay, now nevertheless, this equation only applies for strong electrolytes. You will notice that when you actually plot this, you will figure out there's the odd one out. And no surprise, it will be the weak electrolyte, in this case, the acetic acid. So then how do you actually, so you can't use then, from the plot, obviously you will see that you can't find the value of the lambda naught for acetic acid. So no worries, there's another solution for that for weak electrolyte. So you use the Colebrooke's law. I hope I pronounced that right. So the Colebrooke's law is to be employed to determine the molar conductivity of this. So, so the degree of dissociation for electrolyte, in this case acetic acid, can be calculated by this lambda molarity over that of the dilution. So you will find, from the various solution, okay, the values for the lambda naught for this, and from this equation you can straight away find the value for the conductivity at infinite dilution for acetic acid. Okay, so just use this equation to that. So I do want to mention also that since one of the things that you need to measure is also the dissociate, what do you call the dissociation constant for acetic acid. So you see this equation in your manual. So I just want to highlight that in case that you get this confused, this is actually alpha, and it's just not the right font to use for this symbol. So it's not an A. So the alpha here is given by the molarity, the conductivity, the molar conductivity over that, the molar conductivity of dilution. So the Ka can be measured according to this. Okay, so all you need to do is just plug this into this equation. Remember, this is alpha, this is also alpha. Okay, right, so I don't want to highlight on the experimental procedure. Is pretty much very straightforward. Pretty much all you have to do is actually prepare this. So in the lab you'll be preparing all these solutions, and then you will do the dilution, and then you will start measuring the molarity of this using the conductometer. Okay, and so here are the data by there's a pair of students. The temperature is conducted at this temperature, so the temperature is at this. And so these are the values for the various solutions. Okay, so you have here, and as you can see here, they actually label the table, the caption at the top, as what I mentioned. Okay, so you have here, so the kappa here is also the same. Now if you look at the equation in your lab manual, the kappa is also the lambda. Okay, so you have this the average. You have the average that you have to measure, so you just take this and average this up. Okay, take these values and average this. Okay, and from there you need to measure the molar conductivity, which is equivalent to this over that, and make sure that you convert according to this so that you can see the consistency. All right, so remember that this is in ms and this is in s and m square, so make sure that this is done. And this is just taking the square root of the concentration. So all you have to do is fill in this. Okay, once you have filled in all these tables, okay, what you need to do is, okay, from this and this, so now you can use that to actually plot the molarity, the molar conductivity against the square root of the concentration. And from the plot you can actually measure the molar conductivity at infinite dilution, the lambda naught. Okay, so it doesn't stop there. Okay, so now with those values, so these are the given values in literature, so these are the values that you get from the plot, so just comment on that. Okay, and the temperature is this, and you also can fill in this, that the temperature is that. Now ultimately you need to measure the dissociation constant for acid to acid, and again it's given by this equation. So the molar conductivity, so you have all the concentration, these are from the previous table, so this I'm just taking this from the data sheet. Okay, and then you have this, the molar conductivity of that, and then you have the molar conductivity at infinite dilution, which is actually also, you know, calculated, and you get the value of this alpha from the equation that is given just now, and from that you just calculate the value of this. Okay, and then you just fill in this. Okay, so I do want you to show the calculation, don't just fill in this, but show the calculation as well. And from the plots also do comment on that. Okay, so pretty much that's pretty straightforward. So the report contents will be as usual: title, name, new metric number, new selfie, as I've you know, so that, you know, I see fresh new look every time. The objective, which is already stated, the introduction, which include the theoretical background, results and discussion, fill in the table, plot the graph of that, and the tables calculate also the Ka. All right, and conclusion, and then remember to reference using APA style. So this is due next week then. So again, to this email, and email subject SIC1004 underscore experiment 5. Okay, so pretty much that's it. So till next week, please stay safe. All right, thank you, and assalamualaikum warahmatullahi wabarakatuh.